Alright, so in this video we are going to talk about SOP and POS. And they are pretty important concept for simplified logic expressions, and so we can design a circuit out of it to make a simplified circuit version. So SOP stands for sum of products. So all the computer logic systems, if we can actually think about them as a logic black box, has an input and output. It's just like you have a logic circuit inside and process the different types of combinations of input and give a corresponding output, right? So what is the content inside? You can design it. It's customizable, right? So here is your logic. And we are using a truth table to describe all these possibilities of the input and the corresponding output. A truth table, for example, here we have an example like that. We have 3 inputs and 1 output. So we can start counting all the possibilities or all the combinations for the inputs. They can start from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Totally 8 combinations. It's super simple. You have 3 bits, so it's going to be 2 to the power of 3. This many of combinations for the input. And we don't know what is the logic here, but the thing is the customer already tell you, I need a circuit. They're telling a computer designer to design this kind of logic. When the system has this kind of inputs, you need a certain specific output from the system. Okay, this is a requirement from the customer in the future, for example. So here has to be 0, here has to be 0, 1, 0, and all the rest of them are 1s, right? And we can label, here is M0, M1, smaller case, right? It's case sensitive. Let me label that just in case. They are lowercase. And we label this row as M0, M1, M2, M3, M4, M5, M6, M7. Okay. So the SOP can be written in this following form. We are trying to use the logic expression to cover all these cases. So that logic expression is going to work for all these cases. Doesn't matter if it is 0 or 1. Whatever input being plugged into that logic expression, you should get the correct output. That's the purpose. You cannot change that. That's the bottom line. For the SOP expression, we are trying to use the terms of products, and we sum them together to get the final result. That's why we called it's a SOP form, right? So y equals to, so when you are doing SOP, you only look at the 1s. And you ignore the 0s for now. But however, finally, we can verify that they are also valid for the 0 cases. Yeah, don't worry about that. Let's just do the 1s first. So this is a method how to do that. It's not changing too much, and every time you do it in that way, it's going to be right. And the first time we verify they are valid, so it's going to be valid in the future. So just use it, okay? So we only look at the 1s. So that's the first one here in the result. And we are trying to use, when you see a 0 here for A, and you put an A bar here. And B, if you have a 1 here, you just put a B here. If you have a C, you have 0 for C, you put a C bar. And or the other one, this case, 1, so it's A, B bar, C bar, or A, B bar, C, or A, B, C bar, or A, B, C. That's how you do it. So this one will work for the entire truth table. And we can verify this really quickly. So let's look at the first one. If A is 0, you got a 0 here, but bar, you got a 1, 1, 1. So you got a 1 here. And you can verify all these ones, they will be 1 all the time. So which will be verified for this one, which is actually valid because you are using the results which are ones for these expressions. So if you plug in all these little things into there, and you can verify that they are all ones. Now let's try a 0 case. 0, you got a 1, 0, oops. So 0 is going to be a killer for the AND gate logic. So the entire thing will be 0. It's the same thing as this one. You got a 0 here, 0, 0, 0, 0. So everything will be 0. So that's why the result is 0. The same thing, you can verify by yourself, and it's going to be valid for the entire truth table. So that's the SOP form for this logic. And because we already have the logic expression, it's more friendly for our, for human beings' brain, because we can find out you have 3 inputs and you can design a logic circuit out of it, right? But before we do that, let's see if we can simplify that. Because right now you can see that we have, yeah, let's do it. Let's see what's a circuit. So we have ABC. I'm not sure if I have enough space. So let's see. Probably I can. I don't know. ABC, and I have. Yeah, it's tough. Let's don't do that. A naught, B naught, C naught. So A naught, which is A naught, right? So B naught. So in order to get B, you need an inverter for that. C naught. So all these lines are just metal wires. So that's the signal for A, that's the signal for A bar, B bar, C bar. Okay. And A naught, B, make a connection here, C naught, right? So you have AND logic here, A, B naught, C naught, A, B naught, C naught, A, B naught, C, A, B naught, C, A, B, C naught, A, B, C naught. Finally, ABC, A, B, C. That's how I get the circuit. And just assume we have 5 input OR gate. So probably it's not that practical. We don't do that usually. But let's just assume we have an OR gate. We can get a circuit like that. So that's the circuit to implement this logic expression here. But however, you can see that it's pretty complicated, and we can probably simplify the logic expression and then simplify the circuit further. Now let's see what we can do here. So that's logic expression, and let's see which one we can combine together. Here's a B naught, C naught, A, B naught. So you have this one here, have the common term here, common term. So you can take them out at the same time. And here, same thing here, is there are common terms. So y equals to A naught, keep the first one the same thing here, and then take out AB naught and C naught or C. And here, take AB naught, AB out, and C naught or C. Okay, so that's one, so ignore that. And you get A naught, B, C naught, or A, B naught, or AB. And common terms, so it's gonna be A, B naught, or B, which is 1. So which is A naught, B, C naught, or A. Okay? And now apply that theorem in Boolean algebra. If you forget, just go back to that lecture and look at the notes. So remember that A or B, A or C equals to A or BC. Back and forth, right? So now you have that A or BC, right? A or BC will be A or B and A or BC. No, A or B or A or C, right? So B, B, C. A or BC, A or BC, A or B, A or C. Okay, and that's 1. So finally you have this left. Now I can compare. We can design a circuit from here easily, right? So we have A, B, C naught, 3 lines, right? Just like A or B and C, B and the C naught, sorry, B and C naught. It's going to be Y. And this circuit will do the same thing as this circuit. So you can now find out, you can actually simplify the circuit a lot by using Boolean algebra. And further, you can simplify the circuit, which can reduce the size of the circuit on the integrated circuit chip a lot. So you can integrate more functions. That's why we can have a laptop and smartphone that tiny in size, but can do a lot of things. You can watch videos over there because we can simplify the logic to make it more compact. Okay, that's a pretty good example for showing you how to simplify the logic from the customer's requirement. So customer sends you this logic and asks you to design the circuit to implement that. And actually, you already know how to do it. You get a logic expression, you simplify it, and you get a circuit. And you design that on the PCB board, you can sell it to the customer. Okay. So that's SOP. Excuse me. And there's another form which is called POS. And I'm going to show you what does that look like. So what that looks like. So we are using the same example. So when you are doing a POS, the labels are capitalized M for every row. Not smaller case, but uppercase. Okay, and they are representing it's called max term. I'm going to show you what is that later, but let's do it first. So POS stands for products of sums. So now you are only looking at zeros. And if you have a 0 here, you directly write an A in the term without a bar on the top. So let's show you really quick. So for the first line, since right now we are only looking at the 0 terms, right? So y equals to A or B or C. And A or B or C, when you have 1, you put a bar on the top. A or B bar or C bar. That's how I'll do it. So the next step will be, of course, simplification. And actually, you can verify this really quick by yourself. You just plug in all these values. You can find out this term, it's going to do the same job as SOP. They are going to implement the same logic, but in different types of different combinations of gates. You can plug in all these inputs into this logic expression. You can find out it's going to be valid for all these ones and zeros for all these rows in the truth table. Okay. Now I won't try to verify every single line for you, but you can do it by yourself if you like. But now we know how to do it. We just keep using that conclusion in the future. So it's easier to remember. You don't need to demonstrate every single theorem or laws every time in the calculation. So the next job here is to simplify this. How do you do that? I think we can use the same conclusion we just used. Remember? I'm going to repeat it for you here. A or B and A or C equals to A or BC. Right? So A or B, A or C, you know what's the next step, right? So it's going to be A or BC. So which is 0. Just keep this one the same. We didn't touch it. So now it's going to be A or B not, or C not. Still the same concept. A or B, A or C, right? Equals to A or BC. A or BC. So which is A or? Which is A or? Okay. And I think by chance we get the same simplified version with SOP. It's the same stuff. So we won't. It's the same circuit here. You can do it if you like. And so this is how that works for POS. And now I'm going to summarize for you. When you see this kind of stuff, there are just different representations for POS and SOP. You know what are they, right? So let's come back to the truth table and let me show you how people usually represent this kind of SOP and POS regularly, make it simpler for the readers. So for SOP here, if you get a truth table, people ask you to write an SOP, and the final conclusion should be like that. So here's Y, that's the final result, and you have inputs A, B, C. Okay, they are the variables for this function. You can think about in that way. And this one equals to, for SOP, it equals to the summation of the min terms. What are the min terms? They are 2, 4, 5, 6, 7, parentheses. Okay, that's one form you can represent. And the same thing, you can also do that. That's a summation of what? M2, M4, M5, M6, M7. Either way, okay, you'll probably see these two ways at the same time, but they are doing the same job. POS Y A B C. So they are a product of the sums. So it's a pie, it's a bar and two vertical bars. Here, like look at capitalize the pie, right? So that means it's a product of what? Of the max terms 0, 1, 3. Or you can do it in that way. M0, M1, M3. No. Both ways are pretty valid. You can do it in both. You will see this in the homework, so make sure you understand what are they, so you can do the homework. Okay, so that's the beginning of the introduction of how do we design a digital system by a given logic. They are static combinational logic, and how you do it is you get a logic expression and then you simplify it and then you draw the gate circuit. What are the gates consist of. They are just CMOS transistors. Actually, you are able to build them up in LT-SPICE. So it's from the very beginning to the very end final product. What are they right now? And so here's one thing. This is a really simple circuit and it's easy to simplify. You can eyeball it. So when the logic becomes more complicated, you couldn't do it by Boolean algebra. Then we need another technique to simplify the logic, which is called K-map. Right? Still by manually you can simplify using another technique. So we're going to introduce that in the next lecture. And thank you for watching this video, and we'll see you in the next video.